9, we're really going to get into some juicy stuff. We're going to take power series to represent several different functions. And we're going to start with basic geometric series. So 1 over 1 minus x, that function resembles a geometric series where a here, the first term, is equal to 1, and the common ratio is equal to x. And that's just a basic geometric series, the sum for it, provided the common ratio is less than 1. So this function, f of x equals 1 over 1 minus x, that can be expressed as the sum from n equals 0 to infinity of x to the n. In other words, 1 plus x squared plus so on, provided the absolute value of x is less than 1. This is centered at 0 and has a radius of convergence equal to 1, so this function 1 over 1 minus x is equal to this power series only on the interval -1 to 1, not working on the endpoints. If we want other values of x besides -1 to 1, we have to rewrite this function so that we're using a different value for a and r. So how can we rewrite 1 over 1 minus x so it's centered at -1 instead of at 0? We want to now find the power series for that and the interval of convergence. So we have to manipulate this. We need to get an x plus 1 in here, because x plus 1 means it's centered at -1. So if I have x plus 1 down here, if I add 1, I also have to subtract 1 to keep things balanced. And then this is the same as 1 over 2 minus x plus 1, that quantity. Well, for this to work with the power series, a geometric sum, I need the first term over 1 minus something. Well, I can achieve that by dividing everything in the problem by 2. So I'm left with 1/2 over 1 minus x plus 1 over 2. Now the first term is 1/2, and the common ratio is x plus 1 over 2. So 1 over 1 minus x can be written as the sum from n equals 0 to infinity of 1/2 times x plus 1 over 2 to the n. And this is going to be convergent when x plus 1 is less than 2. Because I can take this common ratio, it will converge when this is less than 1. So I'm left with this. My interval of convergence then is going to be when x is an element of -3 to 1. And if I were to write out this power series, I could write it as 1/2 times 1 plus x plus 1 over 2 plus x plus 1 squared over 4, and so on. So this is the same function, 1 over 1 minus x, but we're not centered at 0 anymore. We're centered at -1. And this series is going to be convergent. It's going to represent 1 over 1 minus x when x's are between -3 and 1. Kind of a neat idea. And we can take it a step further. We want to find a power series for the function 4 over x plus 2 centered at 0. We want to get this into that form, a over 1 minus r. So I need to start manipulating this. I need a 1 minus something on the bottom. Well, I can get a 1 down there by dividing by 2, but I have to do that to everything. So my function is now 2 over 1 plus x over 2. But I need 1 minus the common ratio. So 2 over 1 minus negative x over 2. So 4 over x plus 2 is given by the series n equals 0 to infinity of 2, the first term, times negative x over 2 to the n. This power series would be 2 times 1 minus x over 2 plus x squared over 4 plus x cubed over 8. And this will converge for negative x over 2 being less than 1. In other words, the absolute value of x less than 2, so the interval of convergence is -2 to 2. Another way to find this power series is actually to do long division. I could take x plus 2, I'm dividing 4 by that. 4 plus 0x plus 0x squared plus 0x cubed plus so on. And I'm actually going to change the order just a little bit here. 2 plus x. I want the 2 to become the 4. So to get that I need to multiply by 2. And then I come back to multiply 4 plus 2x. Subtract. And you know what, I wrote down the series incorrectly. Hopefully you caught that. It should have been an alternating series. 1 minus x over 2 plus x squared over 4 minus x cubed over 8, and so on. So now I continue with my long division. I need negative x up here. How do I get 2 to become x squared? Well, I need to multiply by 1/2 x squared. And I could continue on, but you can see that if I factor a 2 out of this, I get 2 times 1 minus 1/2 x plus 1/4 x squared, and so on. I get the same series that I got by rewriting this so it represents the power rule sum, the power series sum. Now let's continue working with some different functions. Let's go with 1 over x centered at 1. So 1 over x, that's equal to, now I want my x to be x minus 1. But if I'm going to do that, I have to add 1 too. And I can simplify this to 1 over 1 minus negative x plus 1. Remember, I want 1 minus r. So the first term is 1. The common ratio is negative x plus 1. And I can simplify this rule to be negative 1 to the n times x minus 1 to the n. It's an alternating series, because this is really negative 1 outside there. So this rule, this series, gives us 1 minus x minus 1 plus x minus 1 squared minus x minus 1 cubed, and so on. And this will converge. It will give us 1 over x for the absolute value negative x minus 1 being less than 1. In other words, just the absolute value of x minus 1 is less than 1. So you can see that this is centered at 1, and it has a radius of convergence of 1. So our interval of convergence will be 0 to 2. And we can get pretty funky with these things by using some real simple rules. If we have 2 power series, we can perform some operations on them. I can write a power series for a function of a scalar multiple of x. I can write a power series of a function of x to an exponent. Or I can write a linear combination of these 2 series. For a sum or difference, the interval of convergence will be the intersection of the intervals for f and g. One thing to note there. And we can use this to work with some more complex things. So we want to write a power series for 3x minus 1 over x squared minus 1. Well, to do this, we need to start with partial fractions. And if we go through the partial fractions process, what you should find is that we get 2 over x plus 1 plus 1 over x minus 1. And these are two things that I can write power series for. 2 over x plus 1 is really 2 over 1 minus negative x. Well, that I can write a power series for. 2 times negative x to the n, or negative 1 to the n, x to the n. This will converge when the absolute value of x is less than 1. So its interval of convergence is negative 1 to 1. The second piece of that linear combination can be rewritten as 1 over the opposite of 1 minus x, or negative 1 over 1 minus x. And this would be negative 1 times x to the n. And this has a radius. This will converge when the absolute value of x is less than 1, giving us an interval of convergence being negative 1 to 1. So, what this tells us, our function, f of x, this is equal to, based on that rule that we had, the property on the previous slide, we take that part plus that part. So 2 times negative 1 to the n minus 1, that times x to the n. And that power series would equal, if we expand it out, 1 minus 3x plus x squared minus 3x cubed, and so on. The interval of convergence is the intersection of the blue and red intervals, which in this case is just negative 1 to 1. So let's take this a step further. We want to find a power series for the natural log of x, centered at 1. Well, earlier in this section, we found that 1 over x was equal to this power series with an interval of convergence being 0 to 2. Well, the natural log of x is just the integral of 1 over x dx. And then, of course, plus a constant. So natural log would be c plus the sum from 0 to infinity of the antiderivative of this, negative 1 to the n, and then we raise the power by 1, and divide by that. And to find c, let's go with something that we know. We know the natural log of 1 is equal to 0. So 0 equals c plus some, but if I'm plugging in 1, I get 0 divided by something, so the sum is 0. So c is equal to 0. So the natural log of x is just the series from n equals 0 to infinity, negative 1 to the n, times x minus 1 to the n plus 1 over n plus 1. And if we write this out, we are given x minus 1 minus x minus 1 squared over 2 plus x minus 1 cubed over 3 minus, and so on and so on. And really, we should be checking the endpoints for this. The previous ones, the endpoints did not give us convergence, but with this one we should check. So this is converging from 0 to 2 because it was the antiderivative of this blue one. So we need to check the two endpoints with our new series. If we check x equals 0, we get the sum negative 1 to the n, negative 1 to the n plus 1 over n plus 1. And this is the series of negative 1 to the n times negative 1 to the n times negative 1. Well, that just simplifies to 1 over n plus 1, the opposite of that. And for this series, we want to compare this to the opposite of the harmonic series, which diverges. And the comparison test that works the best for this is the limit comparison test. So I'm going to take the limit as n goes to infinity of our series rule, negative 1 over n plus 1, times, or I'm actually dividing by the rule for what I'm comparing to, so multiply by the reciprocal, and this limit is equal to 1. So this diverges by the limit comparison test. So x equals 0, we don't have convergence on that end. But now we have to go and we have to check checking x equal to 2, the other endpoint. You find that using the alternating series test gives you a convergent series. So the interval of convergence for this power series for natural log is 0 to 2, 2 inclusive, and the polynomial that we get is this x minus 1 minus x minus 1 squared over 2 plus x minus 1 cubed over 3, and so on. And that's the same thing that we end up with if we find the Taylor polynomial for this. Now we know that this Taylor polynomial, this power series, is convergent for x values between 0 and 2, 2 being inclusive. The last example involves finding a power series for the arctangent of x. And you should try to do this one on your own. What you're going to need to start with is the idea of knowing 1 over 1 plus x. And then you can write a power series for f of x being f of x squared. So you have 1 over 1 plus x squared, and that you can take the antiderivative of to get arctangent. I'd like you to try this one. This is one that we'll go through in class together and work out.